So far as we have been talking about linear forces, we've actually been only looking at something called translational forces, even though we weren't really, calling that or talking about it like that at first. But really the assumption that we've been making is that if we were to have an object and we were to exert a force and that object then would move in a straight line, that we're exerting all of that force at the point of the center of mass of the object. So the center of mass is a point in the middle of the object where the mass is evenly distributed around the outside. So when I exert a force there, the thing goes in a straight line, and we say it translates in space in a linear fashion from one place to another. However, if I were to then exert a force somewhere that wasn't at the center of mass, so let's see, I think right here is about the center of mass, I exert a force right here and it goes a straight line up the page, right? But if I'm to exert a force that's not there at that center of mass, then what ends up happening is that object then rotates about its axis. So in this unit, we're going to talk about that rotational motion and then, walk our way through all the concepts from force to energy to momentum in order to, see how this rotational thing differs. So if I were to exert a force that was somewhere near the edge, right, then that force would cause the object to rotate around its center of mass or some other fixed position. So what that means is, like, right now it's going to rotate about its center of mass, which is right about where I pushed it, right, to make it go straight-ish, right? Or if I were to have some fixed point here that I was to hold down, then it would rotate about whatever that fixed position is. So this is rotational motion. So if we go back and we start thinking about Newton's laws, we know that forces actually cause things to accelerate. But in this case, we have a force, and it is different based on, the amount of acceleration is going to be different based on, at what point we actually apply that force. So when we talk about forces in order to make something rotate, it's really something called torque. And the torque is equal to the force perpendicular to the distance at any point. So with torque, that force has to be perpendicular to d, which is the distance away from wherever the point of rotation is. So if I'm going to quantify torque, let's say there was a downward force right here, it would just be this force times distance. So you have more torque the further away you are, the closer you are, you have less torque. If the torque is ever, or the force is ever at an angle, then you just need to take the sine of that angle in order to find the part that is just perpendicular, so that what would be this component, and multiply by the distance. So when we first began talking about torque, we were just dealing with situations that were in equilibrium, just like when we did Newton's laws, where we had, the sum of all forces is the object's not accelerating, so the object's in equilibrium, we're going to set one force equal to the other. So for cases of torque, what we're really doing is we're going to set the torques equal to one another. So what torques? Because we don't have a right or a left, so the type of torque that we have is either clockwise or counterclockwise. So if I had something like a diving board here, and in the first instances, we would indicate that these diving boards were massless, right? So, and a person were to stand out over here, well, if we wanted to figure out the torque around this point of rotation right here, then we would have to figure out, okay, what makes it go clockwise, what makes it go counterclockwise. So this person's weight right here, if I usually fix my pen in this piece of paper, and it would make it swing clockwise. So the torque and the force times the distance of this person over here would make it go clockwise. That means there must be some other torque, because this thing is in equilibrium and it's not spinning anywhere. So there must be some other torque that's going counterclockwise, which would be the force of this board over here, some distance away from this point of rotation, and those would have to be equal to one another, right? So we're just figuring out clockwise torques and counterclockwise torques and setting them equal. Right, another example would be here. So let's say you had a board and it was hanging from some strings or whatever, and this time let's say that the board actually has some weight to it. So the board has some weight to it or some mass to it. The only thing that's different about this kind of scenario is that the entire weight of the board is all exerted at the center of the mass of the board. So if this was like a 200 Newton board, that means you just have another force right here that is 200 Newtons. So if you wanted to figure out the torques, or this is an equilibrium, and you wanted to figure out torques about this point of rotation, well then this string must be pulling up in this direction counterclockwise, and so this would be pointing down this way clockwise. So the force of this string pulling up times the distance to that point of rotation must be equal to this force pulling down times the distance to that point of rotation. Right? So that was torque in equilibrium. So then if we start to look at torque when we're not in equilibrium, we know that according to Newton's laws, that when you have a net force, right, it's going to cause something to accelerate. And in this case, torques, instead of causing linear acceleration, they're going to cause angular acceleration, right? And we are going to have some sort of velocity to them. So we need a way of measuring or quantifying acceleration velocity in terms of angular stuff. So it really is per radii, so it's like a radian measurement. So angular velocity is this Greek letter omega, which is equal to whatever the velocity is at any one point divided by the radius at that point. So it's just like sort of linear velocity per radians, or speed per radians. And then the angular acceleration would be, that linear acceleration, or the acceleration at that instant divided by per radians, right? So then we know that if there is a net force, well then we do a sum of all forces equals mass times acceleration equation, right? So force translational I wrote here is equal to m times a, where mass really is your inertia, or your resistance to your change in motion. It's the amount of matter that you have in you. So the acceleration is a ratio of that force and that resistance, right? So what is it in terms of angular stuff, right? Well, it is your torque, which is really your force, and then we have your angular acceleration here, times this letter I. This letter I is called the moment of inertia, or the rotational inertia. It really has to do with not just your mass as a whole, but how your mass is distributed around your center of mass, or some point of rotation. So the equation for quantifying that is I is equal to kmr squared, where m is the mass, and r is the radius of the object, and it's always the total radius of the object, right? The k is a constant, which helps to relate the distribution of mass. So whether you're a hoop, or you're a disc, or you're a sphere, or you're a cylinder, all of those different things are going to have a different k. If k is equal to 1, that means that all of the mass in the object is 1 radii away. So if all of the mass were like right here on the outside. So you need to know that k. If the mass is at all distributed on the interior of something that's a circle, then we just need to know that k is something less than 1, right? So they would either have to tell you this, you don't have to have these memorized, you just have to know this, that the k is less than 1 unless all of the mass is all the way on the outside. And so if k is less than 1, then we can make a lot of qualitative justifications, or answer a lot of qualitative questions just knowing that your moment of inertia is going to be smaller for anything that doesn't have the mass all the way on the outside, right? So where that really starts to come in then is when we move to then talking about work and energy. So how we worked through translational and linear stuff is we learned about forces, we learned about equilibrium, we learned about sum of all forces equals mass times acceleration. And then we started talking about work, energy, conservation of energy, and momentum. So we're going to relate all of those things to this as well. So remember that for translational stuff, work is equal to the change in energy, or work translational is equal to force times distance times the cosine of theta. So that's really that is parallel, right? So what is it then in terms of rotational stuff? Well, for rotational stuff, work is equal to something called the change in rotational kinetic energy. So when you do work, we're going to change the rotational kinetic energy by making something speed up as it spins around in a circle. Or we can say that the rotational work is equal to torque, which is equivalent to our rotational sort of force. And the distance that something is rotating is really like a change in the angle, right? This won't be used quite as often as this concept. So now we have a new type of kinetic energy, or a new type of mechanical energy that's included in our calculations. So let's look at how we quantify rotational kinetic energy. So it mirrors our translational kinetic energy, so that is Ke equals 1/2 mv squared. So when we write the equation for rotational kinetic energy, we use 1/2. And remember, mass for something rotationally is that I, that moment of inertia, times the velocity squared. So if we look at an object then rolling down a hill, right? So at the beginning, in terms of conservation of energy, we've stored gravitational potential energy in it. And if it was a translational object, so it just went straight down and it didn't roll at all of that gravitational potential energy just converted straight to kinetic energy. But once we have something start to roll, when something rolls, it's going to have some of that gravitational potential energy turn into rotational kinetic energy as well as kinetic energy, right? So our conservation of energy equation now involves GPE, KE, and RKE. Now, what really makes something roll? Something's going to roll down the hill because there's going to be some friction between the surface of the object and the plane, and that friction happens on the edge. It's actually a pullback, that's a rotation, right? That's going to cause this thing to rotate about its axis because it's not exerted at the center of mass. And then you have some of the weight of the object over here, right, pulling down, making it sort of roll over itself. Okay? We don't really have to quantify any of that, just to sort of conceptually understand where that comes from. So if I wanted to compare different objects, like, say, a hoop or a disc, right? A hoop is going to have, so we're going to have GPE equal to KE and RKE. And then this is going to be GPE is equal to KE plus RKE, right? Now, remember that RKE is based on this I, right? So if you have an object that is a hoop, the I is going to have a coefficient of 1. So it's going to gain more kinetic energy, rotational kinetic energy than kinetic energy. And therefore, hoops are going to reach the ground faster. Actually, I think I missed. No, that's right. So they're going to have more rotational kinetic energy and less left over for kinetic energy, and therefore, the hoop is going to not be going as fast translationally as it hits the ground. Versus a disc has an I that is going to have a coefficient that's less than 1, so we're going to have a smaller amount of rotational kinetic energy and more translational kinetic energy, and so this thing will get to the ground faster, so this is a win, right? So this is going to be going faster translationally as it hits the ground and get there quicker. All right, so then the last thing that I want to talk about real quick is just momentum. Remember that momentum is equal to mass times velocity. So momentum in terms of rotational stuff gets a letter L, which is equal to the moment of inertia I times the angular velocity. And momentum, just like in linear stuff, is always, always, always conserved. So the momentum at the beginning of some scenario must be equivalent to the momentum at some other time within the problem. And remember that the I is kmr squared. So one of the things that could be changing would be the radius of the rotation. We could also change the mass of the rotation, or the mass that is rotating. So if something's spinning around in a circle like this and you add some mass onto it, right? You drop something heavy onto the top of this spinning disc. Well, the mass has just increased, and therefore the velocity, or the spinning velocity, would go down, right? If you have a skater and they're spinning in a circle, right, at first all of their mass is some R, some large R, and then you make this R a lot smaller, it means they're going to spin a lot faster. Right? So that's rotational motion, walking all the way through forces, equilibrium, acceleration, conservation of energy, and then conservation of momentum.